The fact that we can put a force on a wire simply by having current going through it while it's in a magnetic field is a very interesting one. If we have a setup like this, where you have a loop of wire that is A high and B wide, and we want to calculate the force, if we put a force on one side and a force on the other side because of current, we can figure out how much overall torque we get out of the situation. Remember that torque is force times the length of the moment arm. And so if this thing is B wide, then the length of the moment arm would be 1/2 B, because your axis of rotation is in the middle. So if you take this force, which is BIL sine theta, in this case we're going to consider when the wire is just in the plane of the magnetic field. So sine theta is going to be 1. So force is BIL, and the distance is 1/2 B, right? Well, the L, the length, is A. And A times half B, that is half of the area of the rectangle. And so we have a torque of 1/2 B times I times A. 1/2 of the magnetic field times current times the area of the loop. On the other half, we have the same thing trying to get it to rotate in the same direction. And so this thing is going to experience a torque of BIA. Magnetic field times current times area. It's going to rotate, but as soon as it gets to here, it's going to try and rotate back the other way. If you think about how the currents are going with how the magnetic field is set up, you have to flip the current from one side to the other. So the way we do that practically in an electric motor, because that's what we're talking about here, is inside the motor, we have a variety of pieces, including your loops of wire. In this case, there's not one loop of wire, there are many loops of wire, and they're actually set at angles to each other for a variety of reasons we're not going to get into too much. There's a little bearing here so it can spin freely, and down here you have a copper ring that is split into a bunch of pieces. This is called a commutator, and that copper ring interfaces with these two little pieces of graphite right here. They're spring-loaded pieces of graphite. I stick them in, and if I pull back, then they pull back into the middle here. These pieces of graphite are called brushes. Graphite is electrically conductive, and it's very low friction. It's slippery. And so when you put this thing in, it spins on the brushes, and the brushes will automatically flip the direction of current every time the thing runs. So current passing through this thing in between these magnets is the foundation of half of the electrical side of the Industrial Revolution. That is your basic electric motor. And it is a relatively simple device that they can get more complicated if you get into things called brushless motors and things which are controlled much more precisely. But that is half of it. The other half of the electrical side of the Industrial Revolution is the electric generator. Both of these things were invented by Michael Faraday. We'll get to the generator in a bit.